righty. 1 minute left, sorry. This is, I mean, if you're going to do polar and you're going to do volume, then you might as well do the classic one, which is just what's the volume of the sphere. We've done this before in Calc 2, or you may have seen it before in Calc 2 when we did volumes of revolution. You can take half of a circle, spin it around. You'll get a, if you take, yeah, if you took a full circle and spin it around, you sort of get like double the volume because you'd be like overlapping. If you take half of a circle and spin it around, you'll get the entire sphere. So you could do this with the disk method or a washer method or a shell method or whatever. But this one is now just straight up. If I took x squared plus y squared plus z squared equals, and then you can put in, to get a general formula, we've used R too many times, so we'll just use A squared, where you can now specify what the radius is. So there's your sphere. In order to do this, we're going to do half of the sphere, the top half of the sphere, and then we just double it at the end. So in order to get the top half, solve for z. So just bring this stuff over, you get a squared minus x squared minus y squared, and then take the square root. And so when you plot this, you'll get this top half of the sphere, a units out, all the directions in the xy plane down at the bottom. So the shadow region, which we're going to need, this is our region R here, is just the circle of radius A. So just like we characterized this in the last example, the radius is between the functions A and 0, and the angle goes all the way around, 0 and 2 pi. We'll do one that has a hole in it so that we don't always have the 0 every single time. But that's the characterization. So the volume is going to be the double integral of our z, this z function here, over the region dA. So if we convert that to polar, and so rectangular is a nightmare on this one, so I'm not going to do it. We're just going to do polar with the double integral. We need to convert z, so we'll get the square root of a squared minus the square of our cosine squared, or cosine, minus the square of our sine. We're converting x's and y's. The dA has r and dr and d theta. And then the bounds I've already just found, 0 to a for r and 0 to 2 pi for theta. So what we need to do is we need to integrate that. And it looks kind of scary, but maybe not too surprising. We're going to get like our sine squared and cosine squared in there. And in fact, that's what we get. If we multiply this inside part out, we get square root of a squared minus r squared cosine theta minus r squared sine squared theta. And we still have this r dr x2 theta on the outside. So if we factor out minus r from the inside, a squared minus, if you factor r squared out, what are you going to get? Cosine squared plus sine squared. And so that is equal to 1. So there's your simplification, again, just using the fact that we're doing minus r squared times cosine squared plus sine squared. And that part there is 1. Sorry. So all this mess ends up coming down to just this integral right here. And how do you do that? You let u equal a squared minus r squared. D will be negative 2r dr. And so you'll end up getting the integral from 0 to 2 pi. What will this thing become? It will become, well, I have negative a half because of this 2, and this will be u to the negative 2 power. So you've got like this negative a half u to the half power. Oh, and yeah, all right, so fine. I don't know if we want to do it here. Then we're writing on this, we can just squeeze it back in. The total volume, and this actually makes it nice, will be twice this answer because we're only finding the top half of the sphere and we want to know the volume of the entire sphere. And if we double it here, then here's my little sneakiness. I'll just double this, and now I know I need this 2r, so I'm going to double it. I'm going to move that 2 here. So instead of getting the 1/2 on this integral, it's just even easier. I just get minus u squared du on the inside. So when I integrate that, it'll be minus u to the 3/2, and divide by 3/2 or multiply by 2/3. So when I plug that back in, there's lots of these side things going on here. I'll have minus 2/3 a squared minus r squared to the 3/2 power. And I got to plug in 0 and a. So trig identity, transforming everything over, doing a u substitution, plugging everything back in, and I will get the integral negative. When I plug in a, what happens? I'll get a squared minus a squared. So that's 0. When I stick in 0, what I get is I get minus a minus, so I'll get 2/3. And then when I plug in 0, it'll be a squared, but a squared to the 3/2 power. So when you have a square to a 3/2, the exponential rules, you multiply the powers together and you'll have a cubed d theta. That's about as easy as you're going to get. You know, there's nothing in there, so you just integrate and you'll get 2/3 a cubed theta, and then stick in 2 pi. 2/3 a cubed, those are numbers. You integrate theta, and here's our formula. We get 4 pi over 3 a cubed, which you probably may have known that the volume of a sphere is 4/3 pi times the radius cubed. So there's your volume for a sphere, which you may have already known, or you could look it up. But congratulations, you just proved the volume of a sphere formula. It's quite possible in sections 13.5, it's on surface area, so we'll figure out the surface area of a sphere. If you don't know that one, you can look it up, of course, but we can also derive it pretty quickly. All right, let's do a couple problems that are a lot similar to the homework here. 13.3, number 7. And now we'll get one that has a hole in it here. So this one says your function looks kind of ugly, and sometimes they do in order to make the integrals work out nicely. So z is the natural log of x squared minus y squared. And you're on the region between x squared plus 1 equals 1 and x squared plus y squared equals 4. So if you were to plot this surface, natural log function of x squared plus y squared, I don't know what it looks like, so I'm just going to draw the shadow region R, and I know what the answer is. It's going to be the volume relative to that shadow of whatever your surface looks like. So you're talking about x squared plus y squared is 1, and x squared plus y squared is 4, so that's a circle of radius 2. So your shadow region looks like a ring. The fancy term for this is called an annulus. You'll see that more in physics class. And so that's just in the xy plane. That's the shadow. Your surface is above it, or potentially below it if it's negative. In this case, it's not going to be negative. The picture is pretty, I'm not sure exactly. I'd have to plot it out and figure it out. But the volume is just the double integral on that region of your curve, or your surface, x squared plus y squared, the natural log, dA. That's the volume. Now, try and do this doing rectangular coordinates where you have a top curve and a bottom curve. And the answer is well, you'd have to break it up where the top curve is here and then the bottom curve is here. But then in this one, you're going to have a top curve and you're going to have a bottom curve there. But you're also down below going to have like another top curve and another bottom curve. So that's 1, 2, 3, and the same on the other side, 4, 5. You'd have to break it up into 6 separate regions and do 6 separate integrals in order to make this work. And they're all going to be really ugly because this top stuff is like square roots. And they're going to have square roots times natural logs or within a natural log. And that's just a super nightmare. So this one's been set up really nicely that if you do this as far as polar is concerned. Now, what are the curves for R and the thetas for R on this one? Well, everything is set up really nicely for circles. And in polar, the outer circle is just R equals 2, and the inner circle is just R equals 1. So as curves go, again, they look just like numbers, 1 to 2. Theta is wrapping all the way around from 0 to 2 pi. And so if you impose that here, you'll get the integral 0 to 2 pi d theta. So that's the outside one. We'll get 1 to 2 dr. That's that one. But then you also have to remember that dA is not just dr d theta, it also has an r. So those three things together is dA. And now convert the inside. And I haven't left much room, but you probably you need to remember that x squared plus y squared is r squared. So the inside part just becomes the natural log of r squared. So that's the setup. I'm not going to work it all out because that's Calc 2, but the basic idea, right, you do u equals r squared, du is 2r, you're going to have a natural log function, and then you can look that up. It's going to be something like 1/2 natural log of u, and then you look at, it's technically an integration by parts, but you can also just look at the table, plug all those bounds in, and you'll get your volume number. So whatever the volume of this shape is, you can work that out. The hard part here is the set. All right, two more like that. We do this a good bit. We don't write all this stuff out in words. We say, all right, you want to do this integral 0 to 5 negative the square root of 25 minus x squared up to 25 minus x squared, square root of 25 minus x squared of square root of x squared plus y squared. So this represents the volume under a surface above some region. And it's ugly, kind of a pretty mathy book kind of problem, but anyway, in order to do this, we need to work backwards, and we need to find the shadow region. We need to find R. So that means that y is between the two curves, minus the square root of 25 minus x squared and positive 25 minus x squared. And x is between the two numbers, 0 to 5. So I don't think you're going to be able to do this without drawing the picture. So these two curves are the half circles of radius 5. So if you take the positive square root, you get the top. If you take the negative square root, you get the bottom. So we're going to go from the bottom curve to the top curve. But I'm only going to go that from 0 to 5. So we're talking about this side of it. We're only talking about the shadow region there. Now, how does this convert to polar? Well, again, we're back in circles. So R is between the inner circle. There is no inner part, so we're always starting at 0 and going out until we hit the outside curve, which is the circle R equals 5. Now, for what angles, this is a different part. The angles are now from negative pi over 2 up to pi over 2. So the angles will sweep through. Instead of going 0 all the way around, we can go from negative pi over 2 up to pi over 2. If you wanted to go from 0 to pi over 4 and then, like, I don't know how you might be able to go backwards, but we always go this way, so you'd have to worry about putting in negatives. I think it's easier just to use negative pi over 2 to pi over 2. So we're kind of wrapping around here. If we impose that on our integral, that means the integral is now negative pi over 2 to pi over 2, and 0 to 5 for r. So again, it's numbers and curves, even though everything looks like numbers. On the end, we've got r dr d theta. That's what the dy dx becomes dA, and then it becomes r dr d theta in polar. And then we have to convert the inside, but again, x squared plus y squared is r squared. So this inside part here becomes the square root of r squared. Square root of r squared. So that's just 1. So we get this super small integral where it's negative pi over 2 to pi over 2, 0 to 5 of r squared dr d theta. That one's pretty easy to do. Just integrate r, plug in 0 and 5, integrate, get theta, plug in the bounds. And so I'll let you figure that out. 13 is similar, just keep getting more practice here. Y, and now this is going to look, well, this is still not going to be too bad. Y to the square root of 8 minus y squared, x plus y, dx dy. So now these have been reversed here. And again, maybe this integral isn't too bad, but it's still going to have some, it's going to be easier to do than polar. So we want to convert this to find the shadow. What is the shadow region here? X, Y. Okay, so x is between, not 0. X is between y and the square root of 8 minus y squared, but only for the values from 0 to 2. So you have to write out what those two curves are. So we get x equals y on one side, and x equals the square root of 8 minus y squared on the other side. So y equals x, x equals y, that's just the dotted line. X equals this square root. Well, if you square things and move to the other side, it's a circle, but it's because it's the positive x values, it's the right half circle with radius, in this case, square root 8. But now we only want this from 0 to 2, y equals 0 to 2. And it just sort of lucks out that they fit if we set this up right. So I want to be to the left of this line. I want to be to the right of the circle, but I only want to be in there from 0 to 2. So it's this wedge. It's like 1/8 of a pizza here. So if I want to convert that into polar, well, again, it's not hard, is that r is between two curves, theta is in between two values. And whenever you're dealing with circles, the equation looks really nice. For r starts at the origin and moves out. There's no hole in it, so that's going to be 0. The outer curve, since it's a circle of radius square root 8, that's just the curve, r equals square root 8. So the outer one is square root 8. Now, what about the angles? Well, you start at the origin, start at the x-axis, so the angle starts at 0, and it comes up until it hits this angle. And since that's y equals x, that's exactly the 45-degree angle, and therefore theta just goes up to, what am I doing? Pi over 4, looking at the apron. Okay, so now we just need to convert everything over. That means that this volume here will be the integral from 0 to pi over 4 the integral from 0 to square root 8. That's the thetas and the r's. Now I need to convert the rest of this stuff over here. So I'll get r cosine theta plus r sine theta. That's the x plus y. And then the dx dy becomes r dr d theta. We always have this like extra r term. And so, again, that one's not hard to do. Maybe we'll just go ahead and do this one. So we multiply through by r, and we get r squared cosine theta plus r squared sine theta dr d theta. Integrate the r, so you'll get 1/3 r cubed cosine. I guess I could have just factored it out, but that's all right. Plus 1/3 r cubed sine. Evaluate that between 0 and square root 8. So plug that in. Let's go ahead and factor that out. Everything has a third. Everything has square root of 8 cubed. So I guess that would be 8 to the 3/2 power. And then I integrate from 0 to pi over 4 cosine plus sine. So we go 1/3, 8 to the 3/2 power. Integrate cosine, you get sine. Integrate sine, you get minus cosine. Plug in the bound 0 and pi over 4. So we get 1/3, 8 to the 3/2. I think I have enough room. If I plug in pi over 4, it'll be sine of pi over 4 minus cosine of pi over 4, and they're the same. Square root of 2 minus square root of 2. So that's 0. When I plug in 0, I'll get 0 and 1, but it has a negative in front of it, but I'm subtracting it. So it's negative and negative 1. And so I just end up getting 8, 1/3, 8 to the 3/2 units cubed. All right. So a little bit more to ponder there. It's all comes from that one volume equation. Now you just have a third way of writing out what that volume is using polar. It would be nice if you have circles for sure. So I guess that's it for today, for the new stuff anyway. And wanted to open it up to see if you had questions on homework, which according to the schedule, in theory, what day is today? The 16th is 13.1. If you went, oh right, we had a test, but we still have homework to do. No. Yeah, I guess that's what it is. So 12.8, 13.1, any of that, any questions on any of that stuff?
Sorry, can you yeah, 21?
Which one?
21 for 13.1.
All right. Probably going to be one that when we put them, they'll end up sort of coming together nicely in theory. We'll see. Okay, so in both cases, we're integrating 1, which means both of these this is actually an area, and this is an area. So it's like an area of region 1, this area of region 2. You don't actually have to find those areas, but you should keep that in mind. Okay, so this means that x is between the two graphs, negative square root y and square root y, and I only want the part that's between 0 and 1. So if you plot those, this is one of these like sneaky things, right? X equals square root y, just square root both sides, that's y equals x squared. And this doesn't matter if you have plus or minus on it, you get x squared. The reason why you have a minus square root and a positive square root is if you work back the other direction. But in either case, this is the parabola y equals x squared, and we are between them. So we're between the negative square root and we're between the positive square root. So thinking left to right, as you do for x's, but I only want it from 0 to 1. So I'm talking about that region right there is the first area. What about the second area? The second area is, here we go. So the second area is x is greater than y minus 2 and less than the square root of y, but I only want that for y between 1 and 4. So if I draw those, the right-hand side is the positive parabola. The left-hand side, y minus 2, what does that look like? Well, I go 2 units down, and then I draw a line like that. It looks kind of ugly, but between 1 and 4 for y, I'm talking about this. And I'm wondering if do they meet up nicely here? Let's see. So at y equals 1, x is going to be negative 1. So this point right here is the point negative 1, 1. On this curve here, this is the point negative 1, negative 1, 1. So if I then try to put these two regions together, and I don't know if you need to do this or not. Maybe we can just we can just work them out separately. This part's going to be annoying over here, but I think the overall region kind of looks like this on the bottom. Then you continue to follow this up, but from here you follow the line instead. So it's kind of like the parabola. So you get up to height 1. You continue the parabola this way, but then you're adding that part in there. So I don't know if it's going to be good to try and do this all at once. It looks kind of sketchy going on there. I think we may want to still keep it as two answers. But I don't know. Maybe now we put them together. When we break it from the top curve to the bottom curve, you probably want to break it there. So you get like this triangular shape, and whatever that is. Kind of part of the parabolic building thing, but we kind of chopped it off. So this chop off here at least occurs at negative 1. This is at 0. This is at 2. So my true axis is in the middle here. Whereas this point right here, well, that's on the line. If y is 4, then what is x going to be in order to get that? It would be 2. I did draw this backwards. X, let's see, x equals y minus 2. I did draw, no, sorry. I think I probably just screwed this all up. So this is the y equals x plus 2. So that actually does this instead. So, all right, scratch that work. Try again. I think in the first one you do get, okay, so you do get the parabola. That's negative 1 to 1. This is x equals negative square root x. Our brain is just wired to do x equals. We don't like x equals. Again, x is between y minus 2 and square root y. So if I draw this properly this time, then y is between 1 and 4. Then the right side is the parabola that looks like this. What is the left side? Now let's be careful. So y minus 2 equals x means that y is equal to x plus 2. So that's, I go up 2, I'm drawing this line like this. Now it does hit at negative 2, or at negative 1, we're at height 1. So at least they're going to hit at that point right there. How about over here? Where does x plus 2 hit x squared? We've already seen one of the answers, that's at negative 1. The other answer is going to be at No, no. X squared minus 2x minus 2. Is it hit at 2? 2. It's at 2 and 4. Okay. But we only are caring about the part in there. From 1 to 4, from the line to the parabola. So there we go. Put them together this way. So if we do the whole parabola, basically it looks like this. If we draw the whole parabola, we go up 2 units, we draw the diagonal line, talking about that region there. It's been chopped one direction there, but not anymore. So sorry for all the pictures here, but so now looking up left and right, we can see for sure that x is going to go from minus 1 to 2. What are the y curves? Well, the top is the line, so that means that y is going to be less than x plus 2, and it's above the parabola, which is x squared. So that's my characterization where I can put all the integrals into just one. So put both integrals just into one. Can you let me know out of that? Okay. So now if I combine them, I can combine them into one, where x is going from -1 to 1, or to 2, sorry, and y is going from x squared to x plus 2. Draw the picture. I'm learning my own lesson. Hopefully that helps. All right, what else? Any other questions
Sir, I was struggling with question 10.
on that section?
Yes, sir.
All right. Okay. So this says just do the integral. I mean, technically what it's saying is it's broken into the 2 parts for you. So it said, if you put parts A and B together, it really means just find this double integral, or this iterated integral. So what that really means is it means do the inside one first, and then do the outside one. So it's an iterated integral. And part A is basically what's inside the parentheses. So how do you do the integral of this thing with respect to y? Well, there's no y in here. So that means everything right there can be thought of as constant. So there's 2 ways to do that. One is just to say, well, look, since it's a constant, I can just pull it outside. It looks weird. It's the first time you've done this before, but you could just pull that outside and do that integral. So that would be 1 to 2, and you'd have 1 over 1 plus x squared. Integrate this, you just get y. Plug in y equals 0 and y equals x. And you'll get the integral from 1 to 2 of x, and then times 1 over 1. So this will be x minus 0, and then you just put them together. Or if you just like, well, wait a second, this is just a constant, so this is just integrated. It's 1 plus x squared y from y equals 0 to y equals x. And in either case, you'll get the integral from 1 to 2 of x over 1 plus x squared. So I mean that's part A, and so then part B is just the basic u sub u equals 1 plus x squared, du is 2x dx. So this will become the integral of 1/2 1 over u du, which is 1/2 natural log u. Plug everything back in. 1/2 natural log 1 plus x squared. Evaluate it from 1 to 2. So if you get 1/2 the natural log of 5 minus natural log 2 in the end. But the key part here is these partial integrations. Think of anything that doesn't have your variable in it as a constant. It becomes a lot easier.
Thank you, sir.
Yeah. right, what else? We have arrived at slide 20, so regardless of what we do, if we're going to go beyond this, we'll have to like stop and come back. So maybe we probably have time for one more, and then I'll sort of release you to go work on homework, get caught up, give you the gift. Like the only gift I can give at VMI is time. That's all you need. I know we're in the summer, so you should have infinite time, but if you have jobs and chores and internships and whatever other classes, it's like this summer's not supposed to be this busy. Any other like final questions on this?
I just have a comment.
Yeah.
I've always wondered where the volume of the sphere formula comes from,
Yeah.
because it's not as intuitive as like the cylinder. I finally learned it.
Yes. All right, we've made one impact. One light bulb went on today, so yeah, that's pretty cool. Do you know the surface area?
The surface area, isn't it like 1/3 pi r h squared? Or
Nope. So we have another treat coming up. Yeah, it's like 4/3 pi r cubed. The r cubed should make sense because it's cubic units, but 4/3 pi, where the heck did that come from? And we sort of saw where, because we ended up having an r squared inside of our integral, and we integrated to get 1/3 r cubed. So at least that's where the third comes from. The 2 came from, or the 4, where did the 4 come from again? Right. So, right. So yeah, one of the 2 came from the fact that we were doubling the top, and the other 2 came from the fact that the angle was going all the way around. So there's your sort of 4 pi. Your a cubed, 1/3 a cubed comes from the fact that we're integrating r squared, effectively, and so that's where it all comes from. All right, go work on that stuff. We'll reconvene this afternoon. We'll talk about center of mass. So how do you actually calculate center of mass? So think center of mass as you're used to thinking in your engineering or physics classes. And so, things like the center of mass in the circle is in the center. The center of a mass of a rectangle is in the center, like the cross. The center of mass of a nice triangle will be there. But what about the center of mass of a parabolic shape, or even this, like, you know what the center of mass is for a quarter circle or a half circle, or who knows what else. So we're going to do some of those examples, and I think we'll just go kind of pretty formulaic, sort of deriving all of this stuff. So anyway, go work on the homework, and we'll answer more stuff at 2:30. Enjoy the rest of your morning.